There is something passing through this room right now. Not light, not sound, not the slow drift of air through whatever crack is in the wall. Something else. Something that does not slow down for the walls, or the floor, or the ceiling, or the body lying in the dark. It passes through all of it the same way, without friction, without record, without any awareness that you were here at all. Every second, billions of these particles move through your body. Not one leaves a mark. Not one interacts with a single atom of you in any way you will ever notice. They come from all directions, passing through the planet itself as though the planet is not there, and they will keep coming long after this night is over, long after everything you know of has ended. We have spent 90 years trying to understand what they are. We still do not know. That is what tonight is about. Roughly 85% of all matter in the universe is made of this invisible, unknown substance. Everything you have ever seen, every star, every galaxy, every atom of everything, is the remaining 15. The universe built most of itself from something it never showed us. Hello, and welcome to Sidereal. Tonight we are going to spend some time with dark matter, what we know about it, how we came to know it, and why the most important question about it remains, after nearly a century of work, entirely unanswered. If you find this kind of slow, careful exploration useful for sleep or winding down, a like or subscribe genuinely helps the channel. And I am curious where you are listening from. Drop your location and the time in the comments. Now, here are the questions that will run underneath everything we cover tonight. Why do the stars at the edge of every galaxy we have ever measured move far too fast? And what does that say about the shape of the invisible universe? What does a collision between two galaxy clusters reveal that no telescope pointed at the sky ever could? And why, after 40 years of searching with some of the most sensitive instruments ever built buried in mines, chilled to near absolute zero, surrounded by kilometers of solid rock, have we found nothing? By the end of tonight, you will understand why each of those questions is harder than it sounds, and why they are all the same question. Let us begin. The universe has a composition, and it is not what you might expect. The Planck satellite, launched by the European Space Agency in 2009, designed to measure the oldest light in the universe with greater precision than any instrument before it returned its most complete results in 2018. What those results described was a cosmic inventory, not a guess, not a model built from assumption, a measurement of what the universe is actually made of, derived from the fingerprints left in light that had been traveling for 13.8 billion years before it reached the satellite's detectors. The inventory runs as follows. Ordinary matter, the atoms and particles that make up everything you have ever touched or seen or detected with any instrument, accounts for approximately 5% of the total mass and energy content of the universe. Dark energy, the force accelerating the universe's expansion, accounts for approximately 68%. Dark matter accounts for approximately 27%. Everything visible, roughly 1 part in 20 of what exists. It is worth holding that without rushing past it. The periodic table, every element ever catalogued, every star ever named, every planet, every ocean and mountain and person and cell and molecule in every living thing that has ever existed on this world. All of it belongs to the 5%. The tools of physics and chemistry, the ones that let us split atoms and sequence genomes and build the devices you are listening on right now, describe the minority constituent of the universe with extraordinary precision. What they describe is the exception, the edge case, the afterthought in terms of mass. The scale of that 5% number is easy to state and difficult to absorb. Consider what it means in practice. Every tool of science that humanity has developed, every telescope, every accelerator, every spectrograph, every detector, every equation in every physics and chemistry textbook has been built to describe and manipulate ordinary matter. The standard model of particle physics, arguably the most precisely tested scientific theory in history, describes the elementary particles that make up ordinary matter and the forces between them. It has been confirmed to extraordinary precision in experiments at CERN and Fermilab and physics laboratories around the world. It tells us what electrons and quarks and photons are and how they interact, and it is accurate to parts per billion or better in some of its predictions. That entire edifice, everything we have learned about the composition of matter across the history of science, describes 5% of the mass-energy content of the universe. The remaining 95% is described either poorly or not at all. Dark energy, which accounts for 68%, is characterized almost entirely by what it does. It causes the expansion of the universe to accelerate, and almost not at all by what it is. The current best description of dark energy is that it is a property of empty space, a constant energy density associated with the vacuum. But whether this description is correct, or merely a placeholder for something not yet understood, is an open question. Dark matter, which accounts for 27%, is characterized by its gravitational effects and constrained by what it cannot be. But what it actually is remains undetermined. Physics is extraordinarily good at describing the universe. It is extraordinarily good at describing the part of the universe that ordinary matter constitutes. There is also something specific to note about how dark matter's existence was established not through a single dramatic experiment, but through the same answer, appearing independently from three very different directions. Nucleosynthesis constrains the baryon density by working backward from the abundances of the light elements, hydrogen, helium, deuterium measured in the most pristine surviving pockets of the early universe today. The acoustic peaks in the cosmic microwave background constrain the baryon density and the dark matter density by reading the oscillation pattern frozen into the oldest light we can observe. The large-scale structure of the universe constrains the dark matter density by requiring a specific scaffolding to have been in place before the visible galaxies formed. 3 measurements, 3 different physical processes, 3 different observational techniques, 3 different communities of researchers. The same answer from all 3. When independent measurements converge on the same value, the probability that all 3 are wrong, in the same direction that all 3 have systematic errors that conspire to produce the same false conclusion, becomes very small. It does not become 0, but it becomes small enough that the convergence itself is information. This is not proof in the mathematical sense. Science rarely offers that. It is the kind of evidence that changes what a reasonable person is obliged to conclude. The remaining 95% is invisible. Most of that, the 27%, is the thing we are discussing tonight. Dark matter has a working definition, even if it does not have an identity. It does not emit light. It does not absorb light. It does not reflect light. If you aimed a telescope in any wavelength, visible, infrared, ultraviolet, X-ray, radio, you would find nothing. It exerts no electromagnetic force of any kind. What it does is exert gravity. It has mass, it pulls, and through that pull it shapes everything around it. Beyond that, its properties are a set of constraints rather than a set of characteristics. We know what it is not, more than what it is. It is classified as cold, in the cosmological sense. Cold means its particles were moving slowly, relative to the speed of light, at the time the universe's large-scale structure began to form. This matters enormously. Hot dark matter particles moving near light speed would have streamed freely across the early universe, washing out density variations on small scales and preventing structures from forming at those scales. The galaxies we observe would not exist, or would exist in far smaller numbers and different configurations. Cold dark matter clumps under its own gravity, seeding the formation of galaxies from the inside out. The fact that galaxies exist at all, in the numbers and configurations we observe, constrains what dark matter can be. The leading candidates are particles. Weakly interacting massive particles. WIMPs are hypothetical particles with masses somewhere between 10 and 10,000 times the mass of a proton, interacting via gravity and the weak nuclear force and nothing else. They arise naturally in certain extensions of the standard model of particle physics, which gave them an early credibility that had nothing to do with dark matter specifically. Theorists building models to solve a separate problem in particle physics found that those models produced particles with exactly the right properties to be dark matter. That coincidence was taken seriously. Axions are a different class of candidate, far lighter, originally proposed to resolve an unrelated problem in the physics of the strong nuclear force, and now considered plausible dark matter candidates by a different route. Sterile neutrinos are a third option. None of these have been detected. All of them remain hypothetical. What is not hypothetical is the mass deficit. That has been confirmed by 3 independent lines of evidence, developed across different decades, using different instruments and different physics, by researchers who arrived at the same answer from entirely different directions. The first is Big Bang nucleosynthesis. In the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion to occur. Protons and neutrons combined to form the lightest atomic nuclei: hydrogen, helium, 4, helium, 3, deuterium, and lithium-7. The ratios in which those nuclei formed depend with considerable sensitivity on how much ordinary baryonic matter was present at that time. If you increase the amount of ordinary matter, the ratios shift in predictable ways. If you decrease it, they shift the other way. The ratios are not predictions, they are measurements. We can observe the abundances of those light elements in the oldest, least processed regions of the universe today, in the spectra of ancient stars, in the chemistry of the most pristine gas clouds, in the absorption lines imprinted on the light of distant quasars. When you take those observed ratios and run the nucleosynthesis equations backward, you get a baryon density for the early universe that corresponds to roughly 5% of the total energy budget. Not 4, not 8, 5. The nuclear physics is precise enough that it does not leave much room. This closes one of the instinctive early objections to dark matter. People wonder whether the missing mass might simply be ordinary matter we have not seen yet, failed stars too dim to detect, gas clouds too cold to emit, rogue planets drifting between the galaxies. The OGLE survey, the optical gravitational lensing experiment, run from a telescope in the Chilean Andes, spent years scanning the sky for compact dark objects in the galactic halo using gravitational microlensing. When a dark, compact object passes between us and a background star, its gravity briefly bends and amplifies the star's light in a distinctive way. Ogle looked for those amplifications across millions of stars. The EROS program, a French collaboration, did the same from a different telescope. Both found some events. A small population of compact objects does exist in the halo, but nowhere near enough to account for the missing mass. And the nucleosynthesis constraints make the argument more fundamental than a census problem. Even if you could find all the cold gas and dim stars and rogue planets in the universe and add them up, the total would still fall within the 5%. The nuclear physics of the early universe did not produce more ordinary matter than that. Whatever dark matter is, it is not ordinary matter hiding in places we have not yet looked. The second line of evidence is the cosmic microwave background, which we will spend more time with later in this script, because it deserves its own section. For now, the pattern of temperature variations in the oldest light in the universe cannot be reproduced by any combination of ordinary matter and dark energy alone. It requires a non-baryonic mass component. The pattern demands it, in the same way that a fingerprint demands a finger. The third line of evidence is the large-scale structure of the universe itself, the cosmic web of filaments, sheets, voids, and clusters that organizes matter across billions of light-years. When cosmologists run simulations of the universe's evolution, starting from the conditions of the early universe and running the physics forward across 13.8 billion years, the simulations that include cold, dark matter produce a universe that looks like the one we actually live in. The right abundance of galaxy clusters, the right distribution of voids, the right two-point correlation function of galaxies at different scales, the right filamentary structure, connecting clusters across hundreds of millions of light-years. Simulations that remove cold, dark matter produce a universe that looks nothing like ours, smoother, emptier, without the intricate web that organizes the observable universe. Not a slightly different version of the universe we see, an unrecognizable one. These three methods, nucleosynthesis, the microwave background, and large-scale structure, were developed by different communities working on different problems. They converged on the same answer. That convergence is not coincidence. It is the weight of evidence. And yet the thing itself has never been directly detected. There is a reason for this, and it is worth being specific about it. In the solar neighborhood, the immediate vicinity of our own planetary system, dark matter is present but thin. All of the dark matter contained within the orbit of Neptune adds up to roughly the mass of a large asteroid. Locally, we are almost entirely surrounded by ordinary matter. Dark matter grows denser toward galactic centers and thickens most in the halos that surround every galaxy, reaching its greatest concentrations in the nodes of the cosmic web where galaxy clusters accumulate. Here, In the outer arm of an unremarkable spiral galaxy, we sit in the thin outer layers of a dark matter halo immersed in it, passing through it continuously, but not bathed in it the way the rough numbers might suggest. Which brings us back to the body in this dark room. If dark matter is made of WIMPs with a mass roughly 60 times that of the proton, then billions of them are passing through every cubic centimeter of space near you right now. The number passing through a human body each second runs into the billions. Of those billions, a careful calculation suggests roughly 10 would interact with a nucleus somewhere in your body over the course of an average year. One collision every 5 weeks or so. The interaction, if it happened, would deposit a tiny amount of energy, a recoil of a single atomic nucleus, and leave no biological trace whatsoever. You would not feel it. There is no mechanism by which you could. The particle passes through without record. The body does not notice. The room is full of something that has never introduced itself. The first person to look at the numbers and say plainly that there had to be something there to name the gap and refuse to paper over it did so in 1933, using a cluster of galaxies and a mathematical theorem borrowed from 19th century thermodynamics. He was right. No one listened for 40 years. That was partly because the evidence was not yet strong enough to compel a field without a mechanism, and it was partly because of who he was. Fritz Zwicky arrived at the California Institute of Technology in 1925 to study the structure of crystals. He had been born in Varna, Bulgaria, in 1898, the son of a Swiss merchant who had settled near the Black Sea to run a textile business. At the age of 6, he was sent back to Switzerland to live with his paternal grandparents in the canton of Glarus, the traditional arrangement for Swiss families who wanted their children educated at home. He proved an extraordinary student. He earned his doctorate in theoretical physics from the Swiss Federal Institute of Technology in Zurich in 1922, the same institution that had awarded Einstein his degree 2 decades earlier and 3 years. Later, the Rockefeller Foundation, actively searching European physics for talent, offered him a fellowship in the United States. He accepted. He had been brought to Caltech for crystals. He did not stay there. By the early 1930s, Zwicky's attention had shifted decisively to the sky, and specifically to galaxy clusters, the largest gravitationally bound structures in the observable universe. A galaxy cluster is not a single object. It is a collection of hundreds or thousands of galaxies moving together under their mutual gravity, embedded in vast clouds of hot gas, the whole system holding itself together across distances measured in millions of light years. That stability requires mass. The question was always, how much? The Coma cluster sits roughly 320 million light-years from Earth. It contains over 1,000 confirmed member galaxies, dominated by 2 giant ellipticals near its center, surrounded by a swarm of spirals and smaller systems. It has been sitting there, apparently stable, for billions of years. That stability was what Zwicky set out to explain mathematically. His method was the virial theorem, a relationship from classical mechanics, originally developed by Rudolf Clausius in the context of thermodynamics, later extended to gravitational systems. The theorem states that for a system in stable equilibrium, the average kinetic energy of its components bears a fixed mathematical relationship to the average gravitational potential energy. Applied to a galaxy cluster, this means measure the spread of velocities among the member galaxies, measure the spatial extent of the cluster, and you can calculate how much mass must be present to keep the system gravitationally bound. If the system is not bound, if the galaxies are moving faster than the escape velocity for the visible mass, then either the cluster is not stable or there is more mass than can be seen. Zwicky used velocity data published by Edwin Hubble and Milton Humason in 1931. He measured the velocity dispersion of 8 Coma cluster galaxies and found a spread of roughly 700 kilometers per second. He then applied the virial theorem, assuming 800 cluster members distributed within a radius of about 2 million light-years, using Hubble's own estimates of galaxy masses. The numbers came back wrong, badly wrong. To keep Coma gravitationally bound given those velocities, the cluster needed to be roughly 400 times more massive than the total luminous content of its galaxies. He worked through the calculation in different ways. The gap remained. Something enormous and invisible had to be there. He called it Dunkel Materia, dark matter. He published his initial findings in German in 1933, then extended and refined the analysis in an English-language paper in the Astrophysical Journal in 1937. In that second paper, he was careful about what he meant. He listed possible candidates for the dark matter in clusters: cool and cold stars, solid bodies of various kinds, gases. He was not proposing exotic new particles. He did not have the theoretical framework for that. The neutron itself had only been discovered in 1932, and the idea of matter made of something other than protons and neutrons was not yet a conceivable category. He was proposing ordinary matter in forms that did not shine, and he was saying there had to be an enormous amount of it. The response from the astronomical community was, for the most part, silence. This is sometimes described as a failure of imagination, or as the inertia of a field resistant to extraordinary claims. Both things played a role, but there was another factor, one that historians of science have not always weighed fully. Fritz Zwicky was extraordinarily difficult to work with and around. He referred contemptuously in print to the useless trash in the bulging astronomical journals. He accused colleagues, sometimes by name, of stealing his results and suppressing their own failures. He had a particular and lasting antipathy toward Walter Baade, the German-American astronomer who was his nearest colleague at Caltech and who had, in earlier years, collaborated with him productively. During the Second World War, Zwicky called Baade a Nazi in departmental meetings, a charge Baade considered deeply and personally unjust. The atmosphere that surrounded Zwicky was one of perpetual grievance and accusation. Jesse Greenstein, who would later lead Caltech's astronomy division, recalled him without warmth. He was vain and self-centered, Greenstein said, and he made working near him a sustained exercise in endurance. He was also, in the majority of his substantive scientific claims, correct. He had proposed the existence of neutron stars in 1933, the same year as the dark matter paper, and predicted that they would be the remnants of supernova explosions. He coined the word supernova, distinguishing total stellar explosions from the lesser nova outbursts. He proposed that galaxy clusters would act as gravitational lenses, bending light from more distant objects, a prediction confirmed by observation decades later. He suggested that cosmic rays were produced in stellar explosions. He catalogued compact galaxies from his basement office at Caltech in his final years. He was right about most of it. Being right, in Zwicky's company, came packaged with the rest of him, and the rest of him was exhausting in a way that made engagement with his work feel like accepting terms that the field was not prepared to accept. His combative nature contributed directly to the delay. Colleagues did not engage with his dark matter result, partly because engaging with the result meant engaging with Zwicky. Work that might have provoked productive scrutiny instead accumulated in the literature, largely unread and largely untested. It sat there, an uncomfortable calculation that everyone who looked closely could see but that no one was motivated to examine further. Sinclair Smith, working independently at the Mount Wilson Observatory, reached a similar conclusion in 1936, while studying the Virgo cluster, finding a mass-to-light ratio far in excess of what the visible galaxies could provide. He published. The finding was set aside. By the late 1940s, the dark matter anomaly in galaxy clusters was acknowledged in the literature the way an uncomfortable fact sometimes sits in a conversation, present, visible to anyone who looked, and consistently ignored. The reason was always the same one that had stalled Zwicky. There was no mechanism. Non-baryonic matter, matter made of something fundamentally different from protons and neutrons, was not yet a conceivable category. The theoretical architecture needed to make dark matter a serious scientific hypothesis did not yet exist. You cannot search for something if you cannot imagine what you are looking for. The theoretical landscape in which Zwicky made his calculation matters for understanding why the field did not engage with it. In 1933, the conceptual toolkit of physics was different from what it would become in the decades that followed. The neutron had only been discovered the previous year by James Chadwick at Cambridge. The nuclear physics of the late 1940s and the particle physics that grew from it, the framework within which a non-baryonic dark matter candidate could be imagined, did not yet exist. When Zwicky wrote that something large and invisible had to be in the Coma cluster, the only candidates he could genuinely conceive of were ordinary matter in forms that did not shine, cold gas, dark stars, bodies too faint, and too small to detect. He could not imagine a particle that had no electromagnetic interaction at all. Nobody could. The theoretical architecture for that kind of matter would not exist for another 3 decades. This is not a failure of imagination unique to Zwicky. It is simply the shape of what physics knew in 1933. Dark matter, as we understand it today, required theoretical developments that had not yet happened. The community's silence was therefore not purely a matter of personality or professional friction, though those things contributed. It was also a matter of the question having no conceivable answer. A mass discrepancy without a mechanism is, from the perspective of a working scientist, a likely measurement error, not necessarily a paradigm-changing discovery. And Zwicky's measurement techniques, by later standards, were rough. He had velocity measurements for 8 galaxies in a cluster of hundreds. His distance estimate was uncertain. His assumption about how to translate galaxy luminosity into galaxy mass used numbers that were themselves uncertain. The calculation was correct. In its broad conclusion, there is more mass here than we can see, but it was not the kind of precision measurement that compels a field to reorganize around it. Sinclair Smith's 1936 result at the Virgo cluster, arriving independently from a different cluster and a different method, should have amplified the signal. 2 independent calculations, from 2 different researchers, from 2 different clusters, reaching the same qualitative conclusion. That is how scientific evidence accumulates weight. It did not amplify significantly. Smith's paper was received politely and filed. The field continued with other problems. What would eventually matter was not a new calculation. It was a new generation of instruments, and the questions those instruments made it possible to ask with precision. The radio telescopes of the 1950s and 1960s could measure the 21-centimeter emission line of neutral hydrogen across the disk and well beyond the disk of nearby galaxies. The optical spectrographs of the 1960s and 1970s could measure Doppler velocities in the stars of nearby spirals, with a sensitivity the 1930s could not approach. The question of how fast stars orbit the centers of galaxies, a question that in Zwicky's time was barely answerable for the few nearest galaxies, became, over those decades, answerable for dozens, then hundreds. Each answer was the same. The mass was not where the stars were. What eventually made it impossible to ignore was not a new theory. It was a new measurement, done not across clusters of galaxies but inside individual galaxies, inside the galaxies themselves, with an instrument built by one person and used, for more than a decade, by another. The measurement was simple in principle. It asked, how fast do stars orbit the center of a galaxy at different distances from that center? The answer was supposed to be obvious. It was not. Vera Rubin was 10 years old when she found she could not sleep through the night without checking the window. The family had moved to Washington when her father, Philip Cooper, took an engineering position that required the relocation. Her bedroom in the new house faced north. The stars moved in a fixed arc around the pole. She watched them. She started keeping notes. By the time she was 14, she had built a telescope from instructions in a magazine, a cardboard tube, salvaged lenses, improvised mounting, and was photographing star trails from that same window. Long exposures on glass plates, the stars leaving bright arcs as the Earth turned beneath them. She kept those plates for the rest of her life. Her father did not discourage her. He drove her to meetings of amateur astronomers in the evenings and waited in the car while she listened to people who knew things she did not yet know. This was not a small thing. She was a girl in the 1940s interested in astronomy at a time when the people who might have helped her along, professors, program directors, established researchers, almost universally assumed she would find something more appropriate to do. She did not find something more appropriate. She graduated from Vassar College in 1948 as the only astronomy major in her graduating class. She applied to Princeton's doctoral program in astronomy. Princeton did not send a course catalog. When she asked why, she was told that Princeton's astronomy program did not admit women, had not admitted women, and had no plans to admit women. She would learn later that this policy remained in force until 1975. From the Harvard College Observatory, the director Donald Menzel wrote her a letter which was mostly formal, but at the bottom of the page, by hand, he had added, "Damn you women." She enrolled at Cornell instead, to be near her husband Robert, who was beginning a graduate program there in physical chemistry. Cornell's astronomy faculty was small and focused on fundamentals. She completed her master's degree in 1951. She moved to Washington when Robert took a position at Johns Hopkins, enrolled in the doctoral program at Georgetown University, and began taking courses at night. She was 23 years old, pregnant with her second child, studying under the physicist George Gamow, who had previously informed her that wives were not permitted at his lectures. She received her doctorate in 1954. Her dissertation examined the large-scale motions of galaxies and found structure in their distribution more complex than a simple uniform expansion would produce. The result was largely dismissed. She spent the following decade at Georgetown teaching and raising 4 children, all of whom would eventually earn doctoral degrees in the natural sciences or mathematics. She continued to work at the margins of her field on galaxy distributions, on whether galaxies clustered or scattered randomly, on what we would later call large-scale structure, before the phrase had become standard. She presented early findings at meetings of the American Astronomical Society, and received responses ranging from polite skepticism to undisguised condescension. In 1965, she joined the Carnegie Institution's Department of Terrestrial Magnetism in Washington. She was the first female research scientist on the department's staff. It was there that she met Kent Ford. Ford was an instrumentalist of the first order, a physicist who built measuring devices with extraordinary precision. He had spent years developing a new image tube spectrograph capable of recording the spectra of faint objects with a sensitivity that previous instruments could not approach. A spectrograph separates incoming light into its component wavelengths and measures how much light arrives at each wavelength. From a galaxy, the spectrum carries velocity information. Stars moving toward you shift their light toward shorter wavelengths, toward the blue end of the spectrum. Stars moving away shift toward longer wavelengths, toward the red. The magnitude of that shift tells you the velocity. Ford's spectrograph could detect those shifts in objects far too faint for earlier instruments to reach. The question Rubin brought to that instrument was straightforward in principle. How fast do stars orbit the center of a spiral galaxy, measured at different distances from the center? The expected answer was well understood. The same physics that governs the planets of the solar system governs the stars of a galaxy. Mercury, close to the Sun, orbits in 88 days at roughly 47 kilometers per second. Neptune, 30 times farther out, takes 165 years and moves at just over 5 kilometers per second. Outer orbits are slower because the mass that drives them is concentrated near the center, and the gravitational force falls off with distance. Most of a spiral galaxy's visible mass, its stars and gas, is also concentrated toward the center, and so the prediction was clear. Stars near the galactic center should orbit quickly, stars in the outer disk should orbit slowly, and if you plotted orbital speed against distance from the center, the curve should rise steeply and then fall. The expected shape was well established. No one expected it to be wrong. In the late summer of 1969, Rubin and Ford drove to Kitt Peak National Observatory in Arizona, mounted Ford's spectrograph on the 2.1-meter telescope, and pointed it at the Andromeda Galaxy, our nearest large spiral neighbor, roughly 2.5 million light-years away. They developed photographic plates through the night. Between plates, they ate ice cream cones. It was, in retrospect, almost deliberately ordinary. There is something in the ordinariness of that drive to Kitt Peak that is worth holding. 2 scientists, an instrument, a rented vehicle, a mountain observatory. The question they were asking had been asked before and had never been answered properly, partly because the instruments to answer it precisely had not existed, and partly because answering it properly seemed like an accounting exercise rather than a discovery. You measure the orbital velocities at various radii, you plot the curve, you confirm what gravity predicts, and you move on. Rubin and Ford were not going to Kitt Peak expecting to find something new. They were going to measure something that needed to be measured properly. The ice cream cones were Rubin's detail. She mentioned them in interviews. The casual normalcy of a long night at a telescope. Plates went in, time passed, plates came out. The fact that what came out of those plates would eventually be named the most important astronomical discovery of the 20th century by some accounts, and would reshape the entire framework of cosmology, was not visible in the ordinary rhythm of the night. That is often how it goes. The discoveries that matter most tend to arrive without drum rolls. They arrive as a measurement that does not match an expectation, a curve that goes flat when it should fall, a number that is wrong in a way that cannot be dismissed. The drama is visible only in retrospect, when the implications have had time to accumulate into something undeniable. The data did not show what they had expected. The stars in Andromeda's outer disk were moving at roughly the same speed as the stars near the center. Not approximately the same, not within a modest margin, approximately the same speed at all radii. The rotation curve, instead of rising steeply near the center and then falling as it was supposed to fall, was flat. Rubin did not immediately understand what she was looking at. She was explicit about this later, in terms that were unusually direct for a scientist of her standing. Months were taken up trying to understand what she was seeing. One day, working with pencil and paper, she made sketches and suddenly understood it all. What she understood was this. If the only mass in the galaxy were the mass visible in the stars and gas, the stars in the outer disk were moving far too fast to remain in orbit. Nothing in the visible galaxy had sufficient gravity to hold them. They should have been flung outward billions of years ago, scattered into intergalactic space. But they were not scattered. They were orbiting. Something was keeping them in, and that something was invisible. The mass had to extend far beyond the visible disk, in an enormous spherical halo of material that emitted no light. If such a halo existed, its gravity would be present throughout the disk and beyond, providing the force needed to keep outer stars moving as fast as inner ones. The rotation curve would be flat because the enclosed mass kept increasing as you moved outward. Not because the visible stars grew more numerous at the edge, they did not, but because the dark halo kept adding mass at every radius. The invisible component outweighed the visible at every distance from the center. The Andromeda paper was published in the Astrophysical Journal in February of 1970. It was precise and careful. It was not immediately received as a landmark. Some colleagues noted it. Most continued with their own work. Rubin continued with hers. Between 1976 and 1986, she and Ford conducted a systematic survey of spiral galaxies, choosing galaxies of different sizes, different luminosities, different orientations, different distances, ensuring the sample could not be accused of selection effects. In their most widely cited paper, published in the Astrophysical Journal in 1980, they presented rotation curves for 21 spiral galaxies. All 21 were flat, not approximately flat. Flat at every radius measured, extending to the outermost stars and gas clouds their instrument could reach. In the same period, radio astronomers were extending the measurements further. Morton Roberts and Robert Whitehurst had measured Andromeda's rotation in neutral hydrogen, a wavelength that traces the distribution of hydrogen gas, which extends far beyond the visible stellar disk. Their data, published in 1975, showed the rotation remaining flat well past the optical edge of the galaxy, into regions where there were almost no stars at all. The dark component was not merely present within the visible disk, it extended beyond the galaxy's visible edge, into the surrounding darkness. The picture that had assembled by the early 1980s was clear enough that it could no longer be deferred. Every spiral galaxy examined contained far more mass than its stars and gas could account for. The ratio varied. Some galaxies required 5 times as much invisible mass as visible. Some required 10 or more, but the direction of the discrepancy never varied. There was always more. The invisible always outweighed what could be seen. Independent confirmation had by then arrived from a different direction. The X-ray satellites of the 1970s had found that galaxy clusters are embedded in enormous clouds of hot gas, gas heated to tens or hundreds of millions of degrees by the gravitational compression of the pression clusters formation. The temperature of that gas reveals the depth of the gravitational well it sits in. At those temperatures, the gas is moving fast enough to escape, if the gravitational well were only as deep as the visible galaxies could create. It has not escaped. Something is holding it in. The mass deficit that Zwicky had calculated for the Coma cluster in 1933 using only velocity data, and the virial theorem was showing up again in the X-ray temperature maps, confirmed by a method that had not existed when Zwicky made his first calculation. Dark matter had stopped being an anomaly in one man's calculation. It had become a parameter in the description of the observable universe. Rubin was careful, throughout, about the limits of her data. She presented what she had measured, She did not speculate publicly about what the invisible mass might be. She had found the effect rigorously and systematically across dozens of galaxies, and she let the effect stand on its own weight. "We have peered into a new world," she wrote late in her career, "and have seen that it is more mysterious and more complex than we had imagined." She was awarded the National Medal of Science in 1993. She was nominated, with increasing frequency through the 2000s and 2010s, for the Nobel Prize in Physics. The prize is not awarded posthumously. She died on the 25th of December, 2016, of complications from dementia. She was 88 years old. In December of 2019, the Large Survey Telescope under construction on a mountaintop in northern Chile was renamed by an act of the United States Congress. It is now called the Vera Rubin Observatory. Its primary scientific mission includes producing the most detailed map of dark matter distribution ever assembled. The instrument she never saw was named for the woman who demonstrated what it is looking for. What Rubin's rotation curves established, and this is the specific thing that changed, was not merely that galaxies contain more mass than they appear to. It was that the mass distribution of a galaxy is fundamentally unlike what the visible stars would predict. The mass does not concentrate toward the center and thin out toward the edge. It extends. It keeps going. The luminous disk of stars and gas that fills telescope photographs is not the galaxy. It is a small bright thing, embedded inside an enormous invisible structure, held in place by something that emits nothing. That structure did not arrive after the stars. It came first. And understanding what that means requires going back further than Zwicky, further than Rubin, further than any telescope, back to a moment when the universe was 380,000 years old and something important had just ended. The universe, in its earliest hundreds of thousands of years, was not the place we inhabit now. It was a plasma, a sea of charged particles, protons and electrons moving freely, with photons colliding constantly between them. The photons and the ordinary matter were locked together, coupled so tightly that wherever the matter went, the light went too, and wherever the light pushed, the matter moved. For those first 380,000 years, ordinary matter was not free to do anything independently. It was a fluid, driven partly by gravity pulling matter into denser regions, and partly by the pressure of radiation pushing back against that compression. The competition between these two forces produced oscillations, the plasma sloshing back and forth between compression and expansion, in waves that propagated through the early universe the way sound waves move through a fluid. Dark matter experienced none of this. Dark matter carries no electric charge. It does not interact with photons. The radiation pressure that tossed ordinary matter back and forth for hundreds of thousands of years had no purchase on dark matter at all. Dark matter was collisionless in every relevant sense. It simply responded to gravity, and gravity alone. And this means it started earlier. From the moment the universe had cooled enough for matter to dominate over radiation tens of thousands of years after the Big Bang, well before ordinary matter was free, dark matter began responding to the tiny variations in density left behind by the quantum fluctuations of the inflationary epoch. Regions that were fractionally denser than average began pulling in more mass. The increased mass deepened the density contrast. The deeper contrast pulled harder. Slowly, across hundreds of thousands of years, dark matter accumulated into a network of knots and filaments and sheets, building the first large-scale structures from the fine-grained seeds that inflation had scattered. Ordinary matter could not follow. It was still locked to the photons, still oscillating, still caught in the acoustic waves. It could not collapse into the structures dark matter was beginning to build. The light would not let it. At 380,000 years after the Big Bang, when the universe had cooled to roughly 3,000 Kelvin, something changed. At that temperature, protons and electrons could finally combine into neutral hydrogen atoms without immediately being torn apart again. They combined, and when the atoms formed, they no longer interacted strongly with photons. The coupling broke. The photons decoupled from the ordinary matter and streamed freely through the universe. We observe those photons today as the cosmic microwave background, the oldest light we can detect, redshifted by billions of years of cosmic expansion into microwave wavelengths. And in that moment, ordinary matter was released. It had been held back by the light. Now the light left, and ordinary matter, finally free to fall, found a universe that dark matter had spent several 100,000 years reshaping. The gravitational wells were already dug. The scaffolding was already roughed in. Dark matter had done the construction work before the first atom of hydrogen had finished forming. There is a way to feel the weight of this that is easy to miss in a purely abstract description. In the period before recombination, those first 380,000 years, the universe was not silent. It was full of sound, in a physical sense. The acoustic oscillations in the photon-baryon fluid were pressure waves, and pressure waves in a fluid are sound. The universe was ringing, at frequencies far below anything a human ear could register, with wavelengths measured in thousands of light years. The loudest note, the fundamental mode of the oscillation, determined by how far sound could have traveled from the Big Bang to the moment of recombination, had a wavelength of roughly 1.5 million light years. We can calculate it precisely because we know the speed of sound in that plasma, and we know how long the plasma existed before it dissolved. The note is frozen into the cosmic microwave background as the first acoustic peak. Dark matter was not part of that sound. It did not oscillate, it did not ring, while ordinary matter was being pushed and pulled by the competition between gravity and radiation pressure, while the photon-baryon fluid was sloshing back and forth in waves of compression and expansion. Dark matter was but simply falling inward toward the dense regions, deepening the wells, preparing the territory into which the sloshing ordinary matter would eventually be released. This distinction between matter that participated in the acoustic oscillations and matter that did not is not merely a physical curiosity. It is directly legible in the oldest light in the universe. The pattern of the acoustic peaks in the cosmic microwave background, which we will come to shortly, depends on the ratio of oscillating matter to non-oscillating matter. The non-oscillating matter, the dark matter, changes the heights of the peaks in a specific way. Too little of it, and the peaks have one pattern. The right amount, and they have the pattern we observe. This is how we know, from direct observation of the oldest light in the universe, how much dark matter existed when that light was released, not how much dark matter there is now. Though expansion allows us to convert between them how much existed when the universe was 380,000 years old. The number matches what we infer from galaxy dynamics and from cluster observations. The same amount, measured in an entirely different way, from an entirely different epoch of cosmic history. The scaffolding was not just built before the stars, it was built before the atoms. It is also worth being precise about the timescale. The dark ages of the universe, the period between recombination at 380,000 years and the ignition of the first stars, somewhere around 100 to 200 million years after the Big Bang, lasted a very long time by human standards. 100 million years is 100 million years. During that entire period, there was no light from stars anywhere in the universe. The cosmic microwave background was slowly redshifting into the infrared and then into the microwave. The universe was dark in the most complete sense. No stars, no galaxies, no sources of radiation except the fading glow of the background itself. But during those dark ages, dark matter was not still. It was clumping, deepening, pulling. The network of filaments and halos that the simulations show us was assembling in the dark. In a universe that contained no observers and no light sources, guided purely by the physics of gravity acting on the density variations that inflation had seeded. The visible universe we live in, the one filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, is the eventual product of that work done in the dark, before anything existed that could have observed it. You are listening to this in a galaxy that formed inside a dark matter halo. That halo accumulated its mass during a period when no stars existed anywhere in the universe, before the gas that would eventually become the solar nebula was assembled into a disk, before the Earth was built from that disk, before the biological processes that produced your ancestors had begun, before your ancestors had existed, before any living thing had looked up at the sky and wondered what it contained. The dark matter structure that your galaxy would grow inside was already there, already concentrating, already holding the shape that the visible galaxy would eventually fill. The visible universe, the stars, the gas, the dust, the galaxies that fill every deep field telescope image, is downstream of dark matter. Every galaxy we can name formed inside a structure it did not make. The scaffolding preceded the building. and the scaffolding is still there, still holding the building up, still extending far beyond the building's visible edge into the darkness, where nothing emits light and nothing can be seen. Consider what the universe looked like at the moment the cosmic microwave background was released. The ordinary matter was in a nearly uniform plasma, with temperature variations of roughly 1 part in 100,000. These variations were real, the compressed and rarefied regions of those acoustic oscillations. Captured at the moment the light was set free, and they were the seeds from which all structure would eventually grow. But on their own, those seeds were tiny. Given only those density fluctuations in ordinary matter and the ordinary matter's own self-gravity, the structures we observe today could not have grown to their current sizes and distributions within 13.8 billion years. The universe simply would not have had time. The structures are too large, too interconnected, too organized. The calculation closes when you add dark matter. Because dark matter had been clumping for several 100,000 years before recombination, it had already amplified the initial density fluctuations, deepening the gravitational wells into which ordinary matter would fall. When ordinary matter was released from the photons, it fell into a universe that had already been gravitationally pre-organized. It collapsed faster than it otherwise could have, clustered more efficiently, and assembled into the galaxies and clusters we observe on the timescale. We observe them because it was not starting from a nearly uniform state. It was starting inside a framework that dark matter had built. The simulations confirm this in a way that is difficult to argue with. Cosmological simulations that include cold dark matter programs like the Millennium Simulation, run at the Max Planck Institute for Astrophysics in 2005, and its successors reproduce the filamentary web of the observed universe, its cluster abundance, its void distribution, its galaxy populations at different epochs, with a fidelity that has no precedent in the history of theoretical physics. Simulations that remove cold dark matter produce a universe that looks nothing like the one we live in, not a slightly different version, an unrecognizable one. Fewer galaxies, no cosmic web, no filaments, a smoother, emptier, less organized place that would not, in 13.8 billion years, have produced anything we see when we look at the sky. The dark matter halo of the Milky Way extends far beyond the visible disk, perhaps 100 times further in radius. The disk of the Milky Way is roughly 100,000 light-years across. The halo may extend to several 100,000 light-years or more. It was there when the first stars in the Milky Way ignited, 10 billion years ago or more. It was there when the first supernovae scattered the heavy elements that later became planets. It was there when the solar system condensed from a cloud of gas and dust 4.6 billion years ago. It is there now. And its particles, whatever they are, whatever mass they carry, are passing through the planet right now, through the crust and the mantle and the core, through the room, through you. Not one of them announcing its passage, not one of them leaving any record that the instruments we currently know how to build can read. The question is not whether it is there. The question is how we know so much about where it is and how much of it exists and still cannot say what it is made of. Part of the answer involves light. Not the absence of light, which is what dark matter gives us most of the time, but the way light bends when it passes through space that contains mass. Any mass, visible or not. Einstein published the general theory of relativity in 1915, and among its consequences was one that seemed, at first, almost too clean to be real. Mass curves space-time. This is the central claim of the theory, the thing Newton had not said. The replacement of gravity as a force acting across empty space, with gravity as the geometry of the space things move through. A massive object does not reach out and pull on other objects. It deforms the space-time around it, and other objects follow the curves of that deformation. The planets orbit the sun not because they are being pulled, but because the sun has bent the geometry of the space they are moving through, and a circular orbit is the nearest thing to a straight line available in that curved geometry. Light follows the same geometry. A beam of light passing near a massive object does not travel in a straight line. It follows the curve of space-time, bending toward the mass. An observer on the far side of the mass sees the light appearing to come from a slightly different direction than its source. If the mass is large enough, and the geometry is right, light from a single distant source can arrive at the observer along multiple paths, producing multiple images, or arcs, or complete rings. The mass acts as a lens. Einstein calculated the deflection angle for light passing near the Sun and found it was twice the value Newtonian gravity would predict. The test came in 1919, when Arthur Eddington led 2 expeditions to observe a solar eclipse, one team to the island of Principe off the west coast of Africa, another to Sobral in Brazil, and measured the apparent positions of stars near the Sun's edge during totality. The stars were displaced from their usual positions by exactly the amount Einstein's theory predicted. The observation was reported in the Times of London and the New York Times within days. It was the moment physics changed its picture of gravity. Zwicky, in his 1937 paper, the same paper that extended his coma cluster analysis, noted that galaxy clusters ought to act as gravitational lenses for background objects, bending and distorting the light of galaxies that lay far beyond them. He was right, as he frequently was. The first confirmed gravitational lens was observed in 1979, when a double image of a distant quasar was shown to be produced by an intervening galaxy. The first lensed arc in a galaxy cluster, a thin, curving streak of blue light, the distorted image of a background galaxy bent around the cluster's mass, was identified in 1987 in the cluster Abell 370. By the 1990s, gravitational lensing had become one of the primary tools for measuring mass in the universe, and its most important property for studying dark matter is this: it does not care what the mass is made of. A lensing measurement responds to mass. Full stop. Stars, gas, black holes, something entirely unknown. The deflection is determined by the mass distribution, not the composition. This makes it uniquely suited to finding something that emits nothing. Strong gravitational lensing produces visible arcs, rings, and multiple images occurring when a massive object sits almost precisely between a distant source and the observer, and the lensing mass is concentrated enough to produce large deflections. Galaxy clusters are the most dramatic, strong lenses in the universe, massive enough to stretch the images of background galaxies into long arcs that curve across a significant fraction of the cluster's angular diameter. The shapes and positions of those arcs encode information about the total mass distribution of the cluster, independently of whatever the cluster's galaxies are doing. Weak gravitational lensing is subtler and broader. When a mass distribution sits between us and a large population of background galaxies, it distorts the apparent shapes of those galaxies, slightly producing a small, systematic tendency toward particular orientations. No individual galaxy reveals this. Galaxies have their own shapes, and a slightly elongated image might simply be an elongated galaxy. The signal emerges only when you observe many thousands or millions of background galaxies together, and measure whether their apparent shapes are correlated in ways that a purely random distribution would not produce. That correlation, called cosmic shear, is the fingerprint of the mass distribution between us and those distant sources. By the 2000s, weak lensing surveys were producing the first large-scale dark matter maps charts of where the mass is, regardless of whether it emits light. The maps showed the same cosmic web that the simulations predicted: mass concentrated in clusters and filaments, with large voids between them. The visible galaxies sat in the dense regions. The dense regions were where the dark matter was. The two coincided exactly in the way that cause and effect coincide. The Hubble Space Telescope, the Subaru Telescope's Hyper-Suprime-Cam survey in Hawaii, the Kilo Degree survey in Chile, and the Dark Energy Survey have produced dark matter maps of increasing scale and precision. What they find consistently is a dark matter distribution that reproduces the predictions of the cold dark matter model well at large, scales the right filamentary structure, the right cluster masses, the right correlation between the positions of galaxies and the positions of mass concentrations. This is the situation by the time you arrive at one of the most striking single observations in the history of the subject. Not a map, a collision. The bullet cluster is listed in catalogues as 1E0657-5-6. The name everyone uses comes from its shape. When a smaller galaxy cluster punches through a larger one, the hot gas of the smaller cluster is compressed by the encounter into a forward-pointing cone, a shape that, in X-ray imaging, looks like a bullet. The name comes from that shape. The collision that produced it happened roughly 150 million years ago during the Cretaceous period on Earth, give or take, roughly contemporary with the middle of the age of non-avian dinosaurs. Two galaxy clusters, each containing hundreds of galaxies and enormous clouds of hot gas, encountered each other at a combined speed of several thousand kilometers per second. What a galaxy cluster contains, by mass, is worth being specific about. The galaxies themselves, all the stars, all the stellar remnants, all the planets account for roughly 1 to 2% of the cluster's total mass. The majority of the ordinary matter is not in the galaxies at all. It is in the intracluster gas, a diffuse, hot plasma filling the space between galaxies, heated to tens or hundreds of millions of degrees by the gravitational compression that formed the cluster. This gas emits X-ray radiation as a consequence of its temperature. It outweighs all the cluster's galaxies combined by a factor of roughly 5 to 1. And the dark matter outweighs all the ordinary matter gas and galaxies together by a factor of several more. When the two clusters collided, each component behaved according to its own physics. The galaxies passed through each other largely without direct interaction. Individual stars in a galaxy merger almost never collide directly. The distances between stars are vastly larger than the stars themselves, and the galaxies slip through each other the way two swarms of widely spaced objects would. The galaxies were slowed somewhat by their mutual gravitational attraction, but they continued approximately on their trajectories. The gas did not pass through. Gas has pressure, and when two high-temperature, high-pressure plasma clouds collide at several thousand kilometers per second, they do not ghost through each other. They interact, compress, and are dramatically slowed by the encounter, the same physics that governs any two fluids in collision. The gas piled up between the two clusters, compressed and heated further by the shock, forming the bullet-shaped feature that gives the system its name. The dark matter, if it behaves as the models predict collisionless, interacting with nothing except gravity, would simply pass through. Each particle of dark matter from one cluster would move past each particle from the other, as though neither were there. The halos would slow slightly due to gravitational attraction, but they would not collide. They would continue. The observation that confirmed this was assembled from multiple telescopes and published in 2006 by a team led by Douglas Clow of the University of Arizona, with Maxim Markovich of the Harvard-Smithsonian Center for Astrophysics among the principal co-authors. The Chandra X-ray Observatory, launched in 1999 and positioned in an orbit that takes it at times more than a third of the way to the Moon, had observed the bullet cluster for more than 100 hours. The team combined Chandra's X-ray data with optical imaging from the Hubble Space Telescope and ground-based telescopes, and with a weak lensing mass map derived from the shapes of background galaxies. The X-ray data showed the gas, two bright concentrations piled up in the middle of the collision, where the gas clouds had slowed and compressed. The optical data showed the galaxies, two separate populations, one on each side, having continued past the gas. And the weak lensing mass map showed where the gravitational influence was strongest, not with the gas in the middle, but with the galaxies on the sides. The gas and the mass were in different places. The dark matter had gone straight through. The ordinary matter, the gas, which is most of the ordinary matter, had stopped. The collision had physically separated the two components of the cluster, and the separation was there in the image, readable from the light that had been traveling toward us since the Cretaceous. Markovich described the finding plainly. The paper by Clow and colleagues was titled, "Without Decoration, a Direct Empirical Proof of the Existence of Dark Matter." That is a strong claim. The authors knew it. But consider what the image actually demonstrates. The most intellectually serious alternative to dark matter, the idea that apparent mass discrepancies in galaxies and clusters reflect not missing matter, but a modification of the laws of gravity at low accelerations, makes a specific prediction. The gravitational influence of a cluster should always coincide with the cluster's ordinary matter. If gravity is modified but there is no dark matter, the mass is where the ordinary matter is, and the gravity follows it. The bullet cluster does not show that. The gravity is where the galaxies are. The ordinary matter, the gas, is somewhere else. The separation is visible. The only way to explain it within conventional gravity is a large amount of mass that did not interact with the gas during the collision, that passed straight through following the galaxies because it interacts with nothing except gravity. That is dark matter. A second cluster collision designated Max J 0025-1222 was observed in 2008 and showed the same separation between mass and gas. The physics demonstrated by the bullet cluster was not a unique anomaly. It generalized. The moment when the bullet cluster observation was published August of 2006, with immediate press coverage from the Chandra X-ray Center, and NASA produced a response in the astronomical community that was relatively unusual for a scientific paper. The paper's title, A Direct Empirical Proof of the Existence of Dark Matter, was itself unusual. Scientific papers are typically titled with restraint, describing what was measured rather than claiming what was proved. The Cloud team chose a different register, and reviewers let it stand, because the observation justified it. Maxim Markovich, in the press materials accompanying the release, noted that the collision represented the most energetic event in the universe since the Big Bang, a claim referring to the kinetic energy released in the merger, rather than to the radiation energy of early universe events. The Chandra image that accompanied the press release, a composite showing the X-ray gas in pink and the mass distribution from weak lensing in blue, overlaid on an optical image of the galaxies, became one of the most reproduced images in modern astronomy. It is the kind of image that makes an abstract argument visible. The argument the image makes is not subtle. The pink is not where the blue is. The mass is not where the gas is. The two things that should coincide, if there is no dark matter, do not coincide. A careful scientist can question the assumptions that went into making the blue map from the lensing data. A careful scientist can note that the collision speed required for the observed separation may be in tension with the rate at which such events should occur in a standard cosmological model. Both of these are legitimate scientific questions. Neither of them explains away what the image shows. The weak lensing maps produced by the Hubble Space Telescope and the ground-based surveys of the 2000s and 2010s have a particular quality that is easy to overlook in a description of the technique. They are maps of something that cannot be seen. A dark matter map is not an image. There is nothing to image. It is a reconstruction, a mathematical inference, derived from measuring the shapes of millions of background galaxies and computing backwards through the lensing equations to the mass distribution that would produce those shapes. The map shows where the gravitational influence is concentrated, not where anything visible is. You are looking at a map of gravity, and yet the maps are consistent. The same filamentary structure that the cold dark matter simulations predict the cosmic web of sheets and filaments and nodes, the same basic architecture at every scale the maps have reached, is there in the reconstructed mass distribution. The invisible has a consistent shape. The invisible has been there long enough to shape the visible in a way that is legible from hundreds of millions of light years away. The bullet cluster also placed constraints on how much dark matter interacts with itself. Because the dark matter halos continued largely unimpeded through each other, the offset between the mass concentration and the gas concentration is consistent with halos that ghosted through. There was no significant slowing that would indicate strong self-interaction. Dark matter, whatever it is, interacts very weakly with other dark matter, as well as with ordinary matter. It is collisionless in both directions. The universe keeps its records patiently. That collision happened 150 million years ago. The photons recording the event arrived here when our instruments were finally built to read them, 100 years earlier, and there would have been no way to see what the cluster was showing. The opportunity was equally present then. We simply were not ready. What the bullet cluster could not tell us, what no lensing map and no X-ray observation and no rotation curve can tell us, is what dark matter is. Where it is? Yes. How it behaves? Yes. What it is made of? Still no. The answer to that question begins not with a detector underground, but with a satellite and the oldest light in the universe. The oldest light in the universe has been traveling for 13.4 billion years. By the time it reached the Planck satellite, it had crossed the observable universe, been stretched by the expansion of space from visible wavelengths into microwaves, and arrived at the satellite's detectors carrying a map of conditions at the moment of recombination, the moment we visited earlier in this script, when the photons and the ordinary matter parted ways. It had crossed the observable universe, been stretched by the expansion of space from visible wavelengths into microwaves, and arrived at the satellite's detectors carrying a map of conditions at the moment it was released. Before any stars, before any galaxies, before any atoms heavier than lithium. Just plasma, photons, and the barely perceptible variations in density that would eventually become everything. The Planck satellite was not the first to detect this light. That distinction belongs to Arno Penzias and Robert Wilson, who found it in 1965 using a large horn antenna at Bell Laboratories in New Jersey, originally designed for satellite communications. Penzias and Wilson noticed an unexplained microwave signal coming uniformly from every direction in the sky, slightly stronger than their antenna's known noise sources could account for. They checked their equipment. They found a pair of pigeons nesting in the antenna horn and removed them. The signal persisted. It was not the pigeons. It was the thermal remnant of the early universe, arriving from every direction because the early universe surrounded us in every direction, an afterglow from a time when the entire observable universe was a single hot plasma, before the photons were released and the atoms formed. Penzias and Wilson received the Nobel Prize in Physics in 1978. The COBE satellite, launched in 1989, made the first precise measurement of the background radiation's temperature 2.725 Kelvin above absolute zero and confirmed that it was not perfectly uniform. Small variations existed at the level of 1 part in 100,000. Those variations were the fingerprints of the acoustic oscillations in the early plasma, captured at the moment the light was freed. John Mather and George Smoot received the Nobel Prize for that work in 2006. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped those temperature variations across the full sky with considerably greater precision and established the broad outlines of what became the standard cosmological model. Planck, operating from 2009 to 2013, pushed the precision further than any instrument before it. The 2018 data released the final, complete analysis of everything Planck had measured, produced the cosmological parameters that now define our best picture of the universe: 4.9% ordinary matter, 26.8% dark matter, 68.3% dark energy. Those numbers come from reading the pattern of temperature variations in ancient light. Understanding how requires understanding what those variations actually record. When the early universe was a plasma, the competition between gravity and radiation pressure produced acoustic oscillations. The plasma compressed, and then expanded, and then compressed again, in waves. The specific wavelengths at which those oscillations were occurring at the moment the photons were released left a pattern in the microwave background. Regions that were at maximum compression when the light was freed appear slightly hotter. Regions at maximum rarefaction appear slightly cooler. When you measure the temperature across the full sky and calculate how much variation exists at different angular scales, the result is a power spectrum, a curve showing how much temperature variation exists at each scale. That curve has peaks. The first peak, corresponding to variations at a scale of roughly 1 degree across the sky, tells you the total density of matter. The ratio of the first peak to the second peak tells you the density of ordinary baryonic matter specifically. The ratio of the second peak to the third tells you the density of dark matter. Here is why this works. Baryonic matter participates in the acoustic oscillations. It is compressed by gravity and pushed apart by radiation pressure, oscillating back and forth in the plasma. Dark matter does not oscillate. It carries no charge. It does not feel the radiation pressure, and it only responds to gravity. It sits in the gravitational potential wells and deepens them, but it does not oscillate with the baryonic matter. This means the acoustic peaks respond differently to baryonic matter and to dark matter. Adding more baryonic matter changes the heights of the peaks in one way. Adding more dark matter changes them in a different way. The specific pattern of peak heights in the Planck data, the ratio of the first peak to the second, and the second to the third, can only be reproduced by a model that includes a non-baryonic matter component that does not participate in the acoustic oscillations, but does contribute to the gravitational potential. A universe with only ordinary matter and dark energy produces the wrong pattern. Add cold dark matter in the proportions. The data requires roughly 5 parts dark matter for every 1 part ordinary matter, and the pattern fits. Remove it, and it does not. 3 independent measurements made at different epochs of cosmic history, using different physics, return the same answer. The nucleosynthesis calculation constrains the baryon density to 5%. The acoustic peak ratios in the Planck data confirm the baryon density independently and add the dark matter density. The large-scale structure of the galaxy distribution is consistent with both. Each of these measurements could, in principle, have disagreed. they do not. The Planck data also confirmed something that the earlier measurements had only suggested. The cosmological parameters are determined with extraordinary precision. The dark matter density is known to within less than 1%. The locations of the acoustic peaks in the power spectrum are determined to fractions of a percent. We know how much dark matter there is to less than 1 part in 100. We do not know what dark matter is. These two facts sit next to each other without resolution. The measurement is among the most precise in the history of science. The identification is entirely absent. There is a way of approaching what Planck measured that makes the accomplishment clearer. Imagine trying to determine the composition of a meal from a photograph of the steam rising from the pot. Not the pot itself, not the ingredients, just the steam, recorded at a particular moment, in a particular pattern. The pattern of the steam reflects, in encoded form, what is boiling beneath it. The temperature of the liquid, the density of the ingredients, the pressure at the surface. If you understand the physics of how steam forms, you can read the pattern backward and infer what produced it. The cosmic microwave background is the steam. The plasma of the early universe is the meal. The photons Planck measured left the plasma at the moment of recombination, carrying in their spatial distribution the record of every oscillation that had happened in the 380,000 years before they were released. Reading that distribution, measuring the amplitude of temperature variations at each angular scale across the full sky, computing the power spectrum, identifying the peaks is reading backward through those 380,000 years of physics to the conditions that produced them. The power spectrum that Planck measured has been reproduced in papers and textbooks many times. It is a plot of temperature variation amplitude on the vertical axis against angular scale on the horizontal axis, and it shows a series of peaks and troughs, the acoustic peaks, frozen records of the oscillation modes of the early plasma. The first peak is the highest. The second is lower. The third is lower still, but not by as much as a simple model without dark matter would predict. That third peak is where dark matter writes its signature in the oldest light in the universe. Here is the physics. Baryonic matter, ordinary matter, participates in the acoustic oscillations. When a region of the plasma is compressed, the baryons are compressed with it, and the photon pressure then pushes them apart. When the region is rarefied, the baryons are rarefied with it, and gravity then pulls them back together. The oscillation is driven by the competition between these two forces, and baryons participate fully in both the compression and the rarefaction. Dark matter does not participate in the rarefaction phase the same way. It is only gravitational. It falls inward toward the compressed regions and deepens the potential well during compression. But it does not respond to photon pressure. It cannot be pushed apart when the photons push. So during the compression phase, dark matter deepens the well that compresses the baryons. During the rarefaction phase, dark matter does not participate in the expansion. It stays in the potential well. The result is that compressed regions are pulled in more strongly than rarefied regions are pushed out. This asymmetry changes the relative heights of the even and odd acoustic peaks in the power spectrum in a specific, calculable way. In a universe with more dark matter, the odd peaks are enhanced relative to the even peaks. In a universe with less dark matter, they are not. The observed ratio of the first to the second peak and the second to the third pins down the dark matter density. The Planck data determines that ratio to a precision that was unimaginable a generation ago. We know the dark matter density of the universe at the age of 380,000 years to within less than 1%. We do not know what dark matter is. Those two facts are both true. They sit next to each other in the scientific literature, in adjacent columns of the same data tables, without resolving the tension between them. The Planck satellite read the universe's composition from the oldest light available, and the recipe it returned lists an ingredient whose identity has not been established, whose particle properties are unconstrained by direct observation, and whose existence was first inferred from a calculation made in a telescope basement in 1933 by a man who almost no one listened to. For nearly 4 decades, we have been trying to find it. 1.5 kilometers below the surface of the Black Hills of South Dakota, in a cavern carved from the rock of what was, until 2002, the home state gold mine, there is a tank. The tank contains 10 tons of liquid xenon, the element xenon, chilled to -96 degrees Celsius, held in a state between liquid and vapor monitored by arrays of photosensors covering every interior surface. The xenon is purified to a degree of cleanliness that has no parallel in ordinary laboratory work. The trace radioactive contaminants in the xenon are reduced to levels orders of magnitude below what most analytical chemistry can even measure. The cavern above and around the tank is filled with water, a shield against radiation from the surrounding rock. The rock above the water is 1.5 kilometers of Black Hills geology, chosen because that much rock stops cosmic rays. The experiment is called Lux Zeppelin, shortened to LZ. It is looking for weakly interacting massive particles. The logic is straightforward. If dark matter is made of WIMPs, and WIMPs interact with ordinary matter through the weak force as well as through gravity, then occasionally, rarely, but occasionally a WIMP passing through a xenon nucleus should scatter off it. The nucleus recoils. The recoil deposits energy in the detector. The detector records a flash of scintillation light and a pulse of ionized electrons simultaneously, and the ratio of those two signals identifies the type of interaction. Nuclear recoils, the kind a WIMP would produce, are distinguishable from the electron recoils that most background radioactivity creates. The challenge is not finding the signal if it is there. The challenge is suppressing everything else, every stray radioactive decay, every cosmic ray muon, every neutron from the surrounding rock, to the point where a genuine WIMP signal, if it exists, would be visible above the background. The depth is the first line of suppression. At the surface, cosmic rays pass through every square meter of ground at a rate of roughly 10 per second. At the depth of the Sanford Underground Research Facility, the rock reduces that flux by a factor of roughly 10 million. The water shield further reduces the neutron and gamma background from the rock. The xenon's own purity removes the signal that trace radioactive contamination in the detector material would otherwise produce. The direct detection program that LZ represents began in the 1980s with small, relatively insensitive experiments. Each generation since has been larger, deeper, and more sensitive. The Large Underground Xenon Experiment, LUX, operated at the same Sanford facility from 2012 to 2016 and set then-leading limits on how strongly WIMPs could interact with ordinary nuclei. Enon 1T, at the Gran Sasso National Laboratory in Italy, under roughly 1,400 meters of rock in the Apennines, extended those limits. Panda X4T, at the China Jinping Underground Laboratory in Sichuan Province, the deepest underground laboratory in the world, beneath 2,400 meters of rock, continued the search in parallel. LZ combined the teams behind LUX and its earlier British predecessor Zeppelin and began taking data at the end of 2021. Its first results, from 65 days of operation, were published in 2022. Extended results from 220 days of operation were reported in 2024 and published in 2025. The experiment has achieved the most sensitive limits on WIMP interactions with ordinary matter ever recorded, across WIMP masses ranging from roughly 10 times the proton mass up to 10,000 times that mass. The results show no evidence of WIMPs. The history of how sensitivity has improved across the generations of xenon experiments gives a sense of the scale of the effort. The first generation of direct detection experiments, running in the 1980s and early 1990s, was sensitive to WIMP nucleon cross-sections, the measure of how strongly a WIMP interacts with an ordinary nucleus of roughly 10 to the minus 37 square centimeters. This number requires a brief translation. A square centimeter is a familiar area, but 10 to the minus 37 of one is a size that has no intuitive reference point. It is far smaller than an atomic nucleus. It is the kind of number that, when written in scientific notation, is simply accepted as the output of an equation rather than understood in any physical sense. What matters is not the absolute value but how it has changed. Each generation of experiment has improved the sensitivity by roughly 1 to 2 orders of magnitude, by factors of 10 to 100 compared to the generation before. LZ's current results represent a sensitivity improvement of more than 12 orders of magnitude over the first generation. 12 orders of magnitude. That is a factor of a million. If the first experiment had been searching for a sound quiet enough to be heard at 1 meter, the current experiments are searching for a sound quiet enough to be heard from the distance between here and the nearest star. The WIMP has not been found at any of those sensitivities. This matters for how the field thinks about what comes next. The original theoretical motivation for the WIMP, its natural emergence from extensions of the standard model designed to solve the hierarchy problem, suggested that the interaction cross-section should be somewhere in the range accessible to the second and third generations of xenon experiments. When those experiments returned null results, the expectation was recalibrated. When the fourth and fifth generations returned null results, the expectation was recalibrated again. Each recalibration is honest, the WIMP parameter space is large, and the null results have only excluded part of it, but the repeated recalibration carries information. The place in parameter space where the WIMP was most expected to be has now been searched. It was not there. The field has not concluded that the WIMP does not exist. It has concluded that if the WIMP exists, it interacts more weakly than the most motivated models predicted. That is a meaningful statement about the physics. This is not a failure. Every null result is a measurement. Each generation of experiment that finds nothing constrains the allowed properties of the WIMP more tightly. If a WIMP exists with a mass in a particular range, its interaction with ordinary matter must be weaker than the sensitivity the experiment achieved. The map of allowed WIMP properties shrinks with each null result. Large regions that once seemed plausible have now been excluded. The WIMP was attractive not merely because it was a plausible candidate. It was attractive because it arose naturally from theoretical considerations that had nothing to do with dark matter. Extensions of the standard model of particle physics that address why the Higgs boson has the mass it does, the so-called hierarchy problem, predict new particles at the electroweak energy scale, particles whose masses and interaction strengths fall precisely in the WIMP range. The coincidence that particles needed for one reason in particle physics happened to have the right properties to be dark matter was taken as a significant hint. The hint has not become a detection, and the region of parameter space that the coincidence motivated has now been searched and found empty. WIMPs remain possible. The interaction strength required by the current null results is weaker than what the most theoretically motivated models predicted. But models exist in which the interaction is that weak. LZ plans to continue taking data through 2028. More parameter space remains to be explored. But there is a fundamental limit approaching. Neutrinos produced in vast quantities by the Sun, by cosmic ray interactions in the atmosphere, by supernova explosions in distant galaxies interact with matter through the weak force. They produce nuclear recoils in xenon detectors. Their flux is known. At a certain level of detector sensitivity, a xenon experiment will begin recording neutrino-induced nuclear recoils at a rate that cannot be distinguished from a low-mass WIMP signal. This is called the neutrino fog. It is not an engineering limit. It is a physics limit, the point at which a xenon detector becomes a neutrino detector, regardless of how much further the engineering is pushed. The current generation of experiments is approaching the edge of that fog. The next generation will push to the edge of it. If the experiments at that frontier return no detection, the accessible WIMP parameter space will have been exhausted. What that would mean for the dark matter question is a conversation the field has begun having, not yet with urgency, but with the kind of careful seriousness that precedes a change in direction. The search for axions proceeds along an entirely different path. An axion, if it exists, is not a WIMP. It is extraordinarily light, so light that the concept of a particle becomes less useful than thinking of axions as a field permeating space, analogous to how physicists describe some aspects of quantum mechanics. In a strong magnetic field, axions can convert into photons. An axion detector is a resonant microwave cavity, essentially, a metal chamber shaped and tuned to resonate at a particular frequency placed inside a powerful magnet. If axions from the dark matter halo of the Milky Way are passing through the cavity, and if the cavity is tuned to the right frequency, some of them will convert into photons and produce a detectable microwave signal. The difficulty is that the axion's mass is not known, and the resonant frequency that needs to be matched corresponds to the axion's mass. The detector must be tuned to the correct frequency. Since the mass is unknown, the detector must scan through frequency space covering a narrow range of possible axion masses at each setting, then retuning to a different frequency, then scanning again. The Axion dark matter experiment, known as ADMX, at the University of Washington, has been conducting this scan for years. covering sensitive slices of the mass range favored by theory. The haystack experiment at Yale University and the abracadabra experiment at MIT are exploring different parts of the mass range with different techniques. Progress is measured in years per frequency octave. The search is thorough. It is also slow. A separate and more ambiguous signal has been explored by X-ray astronomy. Sterile neutrinos, a hypothetical third type of neutrino, heavier than the known active neutrinos and interacting even more weakly, could, if they exist with the right mass, constitute dark matter and occasionally decay into an active neutrino and an X-ray photon. In 2014, teams using the XMM Newton Space Telescope reported a spectral line at an X-ray energy of 3,500 electron volts, an emission feature present in observations of galaxy clusters and the Andromeda Galaxy that did not correspond to any known atomic transition. If this line were produced by sterile neutrino decay, it would be consistent with a sterile neutrino mass of 7,000 electron volts in a range that could plausibly account for the dark matter density. Some subsequent analyses found the line, others did not. The signal remains unresolved, present in some datasets, absent or marginal in others, with the uncertainties in the X-ray background making a definitive answer difficult to reach with current instruments. The Athena X-ray Observatory, currently planned for launch in the early 2030s, will have the spectral resolution to determine whether the line is real and, if real, whether its properties match what sterile neutrino decay would produce. There is a thread running through all of this, through the xenon tanks and the microwave cavities and the X-ray satellites and the underground laboratories worth naming directly. We have been searching, with instruments of extraordinary sensitivity, for a specific predicted particle for roughly 40 years. The search has not found it. The search has not been wasted. Every null result is a measurement, and the measurement of what dark matter is not is genuine scientific information. But the particle itself, the WIMP that the 1980s thought would probably be the answer, has not appeared. The simplest, most theoretically motivated version of the story has not been confirmed. The field is now searching across a much wider range of possible dark matter identities than it was 40 years ago. Before we set that aside, there is one more story worth spending time with. Not about what dark matter might be, but about whether dark matter is necessary at all. Mordechai Milgrom submitted 3 papers to the Astrophysical Journal in February of 1982. He was based at the Weizmann Institute of Science in Rehovot, Israel, and had recently returned from a sabbatical at the Institute for Advanced Study in Princeton, the same campus where Einstein had worked in his later years, the same enclosed grounds of offices and walking paths where some of the 20th century's most consequential theoretical physics had been developed. Milgrom was not a peripheral figure. He was a technically accomplished and careful physicist who had spent time thinking seriously about the galaxy rotation problem and concluded that the dark matter explanation, while possible, was not the only explanation. His proposal was this: Newton's second law of motion force equals mass times acceleration might not be exactly right in all regimes. Not at the accelerations relevant to everyday experience, not in the solar system, not in the dense inner regions of galaxies, where everything has been tested to high precision. But the stars in the outer regions of spiral galaxies are moving under extremely weak gravitational accelerations. Accelerations smaller by many orders of magnitude than anything accessible to laboratory measurement or solar system observation. Milgrom proposed that below a certain threshold, acceleration roughly 1.2 times 10 to the power of minus 10 meters per second squared, to a number so small it has no intuitive reference point, the relationship between force and acceleration changes. Instead of acceleration being simply proportional to force, it becomes proportional to the square root of the force multiplied by a constant. In this regime, which came to be called deep MOND after the name of the theory, gravity behaves more strongly than Newton predicts. The consequence is immediate. If this modified law is correct, flat rotation curves emerge from the mathematics without any additional mass. You do not need a dark halo. You adjust the force law, and the orbits of outer stars moving slowly under weak gravitational accelerations are explained directly. Milgrom's 3 papers were published in 1983 under the name Modified Newtonian Dynamics, which the field shortened to MOND. The theory made a specific and falsifiable prediction that the orbital velocity of a galaxy at large radii should depend only on the galaxy's total ordinary mass through a precise mathematical relationship. This prediction, called the baryonic Tully-Fisher relation, has been tested extensively. MOND produces it naturally as a direct consequence of the modified force law. Cold dark matter models reproduce it, but only after accounting for how galaxies form and how their dark matter halos are assembled, a process that introduces additional assumptions and tuning. The success of MOND at galactic scales is genuine and should not be understated. It predicts the rotation curves of low-surface brightness galaxies diffuse, dim systems where the stars are spread so thinly across the disk that the outer regions are almost purely in the deep MOND regime, with an accuracy that the standard cold dark matter model has struggled to match without careful adjustment of how dark matter halos are modeled, and it predicts what has come to be called the radial acceleration relation. In 2016, Stacy McGarr of Case Western Reserve University, along with Federico Lelli and James Schombert, published a paper in Physical Review Letters analyzing the rotation curves of 153 galaxies from a carefully assembled database called SPARC, the Spitzer Photometry and Accurate Rotation Curves dataset. What they found was a remarkably tight correlation across every galaxy type, every galaxy mass, every galaxy size in their sample. The observed centripetal acceleration of stars at any radius was tightly predicted by the gravitational acceleration that would be produced by the visible mass alone, the stars and gas, even in galaxies where the dark matter is supposed to dominate. The correlation held across 5 orders of magnitude in acceleration, with a scatter far tighter than the scatter expected if dark halos assembled independently from galaxy to galaxy. MOND predicts this correlation as a necessary consequence of the modified force law. In the cold dark matter framework, it requires explanation. Dark halos must be assembled in a way that maintains a tight relationship between the visible mass distribution and the total mass at every radius, across every galaxy type. That relationship is not obviously required by the physics of dark matter halo formation. It needs to be produced by the details of how galaxies form inside their halos. Reproducing the observed tightness of the correlation has been an active challenge for galaxy formation models. There is a specific observational detail about the radial acceleration relation that the numbers make clearer. McGarr and his collaborators found that the correlation between observed acceleration and the acceleration predicted from visible matter alone holds across more than 5 orders of magnitude in acceleration from fast-moving inner regions of high surface brightness galaxies, where baryonic matter dominates and the accelerations are high, all the way to the outer edges of low surface brightness galaxies, where dark matter supposedly dominates and the accelerations are extremely weak. Across that entire range, the relationship is the same tight curve. The scatter around the curve is smaller than the measurement uncertainties in many cases. This is a striking fact. In the cold dark matter picture, the tightness of this correlation requires that the relationship between a galaxy's visible mass and its dark matter halo be very precisely maintained, that galaxies of a given luminosity consistently have dark halos of a specific mass and profile, with very little scatter from galaxy to galaxy. This is not impossible within the dark matter framework. It could emerge from the physics of how galaxies form, from feedback processes that connect star formation to the depth of the gravitational well, in a way that enforces a tight mass-to-light ratio. Galaxy formation simulations have made progress in reproducing the relation, but the tightness is not predicted from first principles the way MOND predicts it. It requires explanation. MOND does not require the explanation because the correlation follows directly from the modified force law. At high accelerations, the modification is negligible and the dynamics are Newtonian. The visible mass fully accounts for the motion. At low accelerations, the modification takes over and the dynamics become MOND-dominated, but the modified force law is still determined by the visible mass alone. In both regimes, and in the transition between them, the observed acceleration is a function only of the visible mass. The tight correlation is not a coincidence to be explained. It is a consequence. The difficulty is that galaxies are not the whole universe. Clusters are part of the universe. The microwave background is part of the universe, The large-scale structure is part of the universe. A theory that works beautifully at the scale of individual galaxies and fails at larger scales is not a complete theory of gravity. It is, at best, an approximation of something deeper that no one has yet found. Milgram has acknowledged this. The relativistic extensions that might complete the theory are active research programs, not finished work. This is a real tension. Serious cosmologists on both sides of the debate acknowledge it. It is not a peripheral argument. But MOND faces difficulties at scales larger than individual galaxies, and those difficulties are severe. The first is galaxy clusters. The same mass deficit that Zwicky identified in the Coma cluster in 1933 is not resolved by MOND. The velocity dispersions of cluster galaxies require far more mass than the modified force law can provide from the visible galaxies alone. To make MOND work in clusters, a component of additional undetected mass is required, often proposed to be massive neutrinos distributed through the cluster. The theory introduced to eliminate the need for invisible mass ends up, at cluster scales, requiring invisible mass of a different kind. This is not fatal to the theory, but it is awkward. A hypothesis that set out to explain mass discrepancies by modifying gravity needs to invoke mass discrepancies it cannot explain. The second difficulty is the cosmic microwave background. The acoustic peak ratios in the microwave background, those features in the Planck data that encode the universe's composition, arise from oscillations in the early plasma. The relative heights of those peaks require a non-baryonic mass component that does not oscillate with the photons. MOND, in its original formulation, is a modification of Newtonian dynamics at low accelerations. It says nothing about the early universe, the physics of the plasma, or the acoustic oscillations. Relativistic extensions of MOND have been developed, Jacob Bekenstein's tensor vector scalar gravity, and newer frameworks, but reproducing the full pattern of Planck's acoustic peaks without any dark matter has proven very difficult. The early universe physics that the microwave background encodes is hard to explain with a modified force law alone. The third difficulty is the bullet cluster. If dark matter does not exist and gravity is modified, the gravitational influence of a cluster should coincide with the cluster's ordinary matter. The bullet cluster shows the gravitational influence on the sides, where the galaxies are. The ordinary matter, the gas, is in the middle, where it stopped. The separation is visible. MOND does not explain it naturally. Defenders of MOND have responses, arguments about the lensing analysis and the collision geometry, but those responses require the situation to be substantially more complicated than the observation straightforwardly suggests. The field's considered position is that cold dark matter explains more phenomena across a wider range of scales, with fewer additional assumptions than MOND requires. Dark matter explains galaxy rotation curves, cluster dynamics, the CMB, large-scale structure, and the bullet cluster, the rotation curves, requiring that dark matter distributes itself in halos with specific density profiles, which is supported by simulations. MOND explains galaxy rotation curves and the radial acceleration relation naturally, but cannot fully account for clusters, the CMB, or direct evidence like the bullet cluster without significant additional machinery. Milgram's papers are more than 40 years old now. He continues to work on the theory, extending it, testing it against new observations, developing the relativistic frameworks that might eventually make it competitive at all scales. A community of careful researchers finds the galactic scale successes compelling enough to continue that work. The debate is not entirely settled, but there is something worth holding in the fact that it exists at all. We are not in a situation where the evidence for dark matter is so overwhelming that no alternative has ever been seriously entertained. We are in a situation where the evidence for dark matter's existence is very strong, and the evidence for what dark matter is remains entirely absent, and in that gap, a serious physicist found room to propose that we might instead be misunderstanding a law of motion that has been in use for 3.5 centuries. The gap is real, the uncertainty is real. MOND is a reminder of both. Whatever you conclude about the theory itself, the honest inventory of where we stand is this. We know dark matter exists. The evidence from nucleosynthesis, the cosmic microwave background, the large-scale structure of the universe, galaxy rotation curves, And the bullet cluster converges on the same answer from directions that have nothing in common except the anomaly they keep finding. We know how much of it there is, to within less than 1%, from the Planck data. We know it is cold and collisionless and non-baryonic. We know it clumped first, built the gravitational framework into which ordinary matter fell, and is present today in halos surrounding every galaxy we can observe. We know it is passing through the room you are in right now, and through your body, and through the planet beneath you, billions of particles every second, leaving no mark. We do not know what it is. 40 years of direct detection experiments have found no particle. The WIMP, the most theoretically motivated, most extensively searched candidate, has not appeared. The Axions search continues, scanning slowly through frequency space, covering a fraction of the allowed mass range. The sterile neutrino signal at 3,500 electron volts remains unresolved. The Vera Rubin Observatory has begun its 10-year survey of the sky and will produce dark matter maps of unprecedented detail. But maps tell you where dark matter is, not what it is. What remains is the question itself, unchanged in its essential form since Zwicky named the gap in 1933. The universe built most of itself from something we cannot see, cannot catch, and have not yet been able to name. We have spent nearly a century learning the shape of a problem without arriving at its solution. That is not a failure of science. It is where science actually lives in the space between what the evidence requires and what we can yet explain. Think about the room you are in, not in the abstract, the specific room. The walls, the ceiling, the floor, the objects in it that you know are there even in the dark, because you have seen them so many times that the darkness does not change their presence. The air, the temperature, the particular quality of quiet that belongs to wherever you are at this hour. All of it is ordinary matter. Every surface, every object, every atom of the air drifting slowly through the room, it is the 5%, the exception, the minority constituent of a universe that made most of itself from something else. That something else is here too. It is moving through the walls right now, through the floor and the ceiling and everything you cannot see, through you, through every cell of your body, through the spaces between atoms that are immensely larger than the atoms themselves, through the carbon and the oxygen and the hydrogen that make up most of what you are, billions of particles per second, none of them slowing, none of them leaving any mark that instruments we currently know how to build can detect. Somewhere beneath the Black Hills of South Dakota, in a cavern carved from rock that was once a gold mine, 10 tons of liquid xenon sit in the dark, cold and still and listening. The photosensors covering the inner surface of the tank are waiting for a flicker of light, a pulse of ionization, some small signal that would be the first recorded interaction between a particle of dark matter and a nucleus of ordinary matter. As of the most recent results, nothing has been recorded. The instruments continue. The dark matter halo of the Milky Way, the enormous invisible structure that surrounds and contains the luminous disk of stars, extends perhaps 100 times further from the galactic center than the visible galaxy does. The disk is roughly 100,000 light-years across. The halo extends to hundreds of thousands of light-years in some models. It was there when the first stars in the galaxy ignited 10 billion years ago. It was there during the cosmic dark ages that preceded those first stars, when the universe contained only hydrogen and helium gas, falling slowly through the gravitational wells that dark matter had spent hundreds of thousands of years digging. It will be there long after the last star in the Milky Way burns out an event, perhaps 100 trillion years from now, because dark matter does not burn. It does not fuse. It does not exhaust itself. It simply continues, present and dark and patient, in a way that the luminous universe, with its cycles of ignition and collapse and remnant, cannot match. The structure that built the scaffolding is still holding the building up. We have mapped its distribution across billions of light years. We have measured its density to fractions of a percent. We have watched it stay behind when ordinary matter was compressed and slowed in the collision of two galaxy clusters, while the dark matter continued straight through. We have read its signature in the oldest light the universe has produced. We have built instruments of extraordinary sensitivity, placed them in the deepest holes we could find, chilled them to temperatures near absolute zero, and asked them to record the moment when a single passing particle announces itself to ordinary matter. Nothing has announced itself yet. Roughly 85% of all matter in the universe is this thing. Everything ever seen, every star ever named, every galaxy ever photographed, every atom in every object in the room you are in is the remaining 15. The universe built most of itself from something that has never been identified. Something that is here, in the room, moving through you, asking nothing and leaving nothing, as it has been doing every moment of your life, and long before your life began. We know it is there. We do not know what it is. That is where tonight ends. Not because the question has been answered, but because it is the honest place to stop. The experiments are running. The instruments are cold and listening. The sky, outside wherever you are, is full of galaxies strung along dark matter filaments that were laid down before any of those galaxies existed. The room you are in is full of something that science cannot yet name. It is passing through you now. Good night.